there any questions on this though? Again, the notes are in your, what do you call it? I emailed it to everyone as a PDF. Okay. Okay, so here's another one. This one I think is actually more like, I think they do this kind of lottery now. Here they have 48 balls, and each ball has a number on it, 1 through 48. So what happens is, I guess somehow through a machine, I think what the machine does, it gives you back 6 different balls. Each one has a number on it. And if the 6 numbers you chose are the same as the 6 numbers the machine gives you back on those balls, then you win $1 million. I think this lottery they still do. And let's say again, I'm pretty confident this is true also, that the order doesn't matter. All they care about is that the 6 numbers the machine gives you are the same. So the order doesn't matter. And since all the balls are different, the numbers, there's no repetition. So we want the probability of winning this if you buy 1 ticket. Okay. So because of that, we want the probability of winning if we get 1 ticket. Okay. Well, we need to know how many different sets of numbers there are. Since there are 6 different numbers, since each set of since each set has 6 different numbers, right? And order doesn't matter, and there's no repetition, we have this. That's our sample space. Our sample space is all the sets of 6 different numbers, as you can see. Okay, so what's the probability of winning then? Well, we only buy 1 ticket, and there's only 1 set of winning numbers. So the probability of winning then would be 1 out of this. We want to get that 1 winning set. And so this is the probability of winning. Awesome. So does this make sense? I hope it does. Now the next one's going to be a little bit different. Okay. Let's modify this a bit. Let's say if it turns out that if you happen to have 5 of those 6 winning numbers, right? Then you win $1,000, let's just say. Okay, what's the probability of winning $1,000 then? Only if, again, you just buy 1 ticket. And again, the ticket you buy has the 6 numbers that you chose. That's how the lottery, I guess, is done. Okay, well, again, our sample space is the same, right? We're looking at all possible sets of 6 different numbers. Order doesn't matter, and repetition is not allowed. So our sample space is the same. What we want, though, is what's the probability of having 5 of those 6 winning numbers? Well, for that to happen, right, we need to have 5 of those 6 winning numbers. Let me show you. 1, 2, 3, 4, 5, 6. So let's say it really doesn't matter what order they're in. Let's just consider the first 5 then. So these 5 have to be 5 of the 6 winning numbers. How do we get that? That's what C of 6, 5 is. Right? Of the 6 winning numbers, we need only 5 of them. No repetition, and order doesn't matter. But you can also see, though, that what about the last number here, right? Well, remember, we don't want the last winning number because we want the probability of winning only $1,000, of only having 5 of the 6 numbers. So we want this number to be one of the losing numbers. How many losing numbers are there? There's 42. There's 6 winning numbers. The other numbers are losing numbers. So any of the 42 remaining numbers can go here. Okay, so for the first 5, we have C of 6, 5. And for the last one here, we have C of 42, comma 1. Although this is really the same thing as 42, so I probably just should have written that. But it's the same thing. You know, we have 42 numbers. We just want to choose one of them. And by the counting principle, we just multiply. That's how many favorable outcomes there are. So the probability of this, we have this quotient divided by this sample size, and we get this. So basically, that's the probability of getting 5 of the winning numbers. Exactly. I hope that make sense. If it doesn't, please don't be afraid to speak up. I like questions. If you don't have any, that's fine also. Okay. So we have that. So let me see. We just that one. Okay, let's do another combination example. Okay. So I have this here, but we'll get to that. So here we're basically playing a card game. There's 52 cards in the deck. And let's say we get dealt or we're drawing 5 cards at random somehow. You know, like poker, for instance. I think in poker they do that. They do 5 card. I think it's called 5 card poker or something. Now the order doesn't matter. You know, to get the winning hand or to win whatever, you have to have the cards, but it doesn't matter what order you get them in. Not only that, the cards are being drawn without replacement. You know, the cards you get, you don't put back into the deck. You hold on to them. Okay, that's cool. So let's find the probability of getting exactly 3 aces. Okay, we want exactly 3 aces in our hand of 5 cards. Now again, we don't care about the order and we don't want repetition. So for the aces alone, there's 4 aces in the deck. To handle that, we have C of 4, comma 3. Okay. And then for the remaining 2 cards, remember, we have to handle all 5 cards. And the last 2 cards, neither of these can be an ace. We only want 3 aces. So these cannot be an ace. Either one of these. Well, there's 48 cards that are not aces. So to handle those 2, we have this. Okay, so how do we get all possibilities? Well, you can think of this as 2 tasks. The first task is handling the aces. The second task is handling the 2 cards here. We have this product. So by the basic counting rule, we're just multiplying. Okay. We're just multiplying. Okay. All right, that's cool. And then, of course, the sample space is all all five. I guess all hands of 5 cards, if that makes sense. That's what this is. Again, the order doesn't matter. And replacement, you know, without replacement, there's no repetition, that is. So the probability would be this. You know, this is the way you can get 5 cards at a time without order and without replacement. So the probability would be this quotient. This product is equal to this. Okay, that's good. Okay, now let's consider this example. Let's now find out. So again, it's the same game. You're getting 5 cards at a time. What is the probability of getting exactly 3 aces and 2 kings? And 2 kings. Well, again, the first 3 cards being aces, we actually saw how to handle that. That's C of 4-3. Now we also want the last 2 cards to be kings. How do we handle that, though? Well, there's 4 kings in the deck. We only need 2 of them. We don't care about order. There can't be repetition. So for the kings, we have this. Okay, so for the first task, we would handle the aces. The second task, we would handle the kings. Now, this is the number of ways. The first task, the aces can occur. This is the number of ways we can get the kings. Second task. So in total, by the basic counting rule, we multiply. This is how many possible hands we can get with exactly 3 aces and 2 kings. Okay, so again, we're still getting 5 cards at a time. So our sample space has this many items. How many outcomes? This is how many outcomes we have. So altogether, the probability, we multiply on top and divide on the bottom. And we get this, which is pretty low. Okay, so we have that example. Let me see what's on. I guess. Oh, darn it. All right, so we have that.